Hello everyone and welcome to session 1 of our operating system course. In this session, we are going to build a solid foundation starting with what our operating system actually is, moving through computer system organization and finishing with the computer system architecture. By the end of the lecture, you will understand how computer hardware and software work together, what the operating system's job really is, and how different system architectures from a single processor to large clusters are built. Let's get started. Let's begin with the most basic question. What exactly is an operating system? In simple terms, an operating system is a program that acts as an intermediary between the user of a computer and the computer's hardware. Think of it as a translator and a manager rolled into one. It sits between you and the raw electronics, so you never have to talk to the hardware directly. More formally, an operating system is system software that manages computer hardware and software resources and provides common services for computer programs. Every operating system is built around three core goals. First, it needs to execute user programs and make solving user problem easier. Second, it needs to make the computer system convenient to use. And third, it needs to use the computer hardware in an efficient manner. Keep these three goals in mind. They are really the philosophy behind everything an OS does. Let's visualize this with a diagram. On the left, you can see the operating system sitting right at the center, connected to your monitor, keyboard, mouse, printer, disk drive, and your applications. Every one of these components talks to the operating system, not directly to each other. The OS is the hub. On the right, we have a more structured view. At the top, we have users, user 1, user 2, up to user n. Below that is the software layer, which is split into system software and the application software. And both of these ultimately rely on the operating systems to function. Below the operating system is the hardware layer, CPU, RAM, and I/O. So the flow is simple. User interacts with the software. Software relies on the operating system. The operating system controls the hardware underneath. Just so this doesn't feel abstract, here are some operating systems you have probably used or at least heard of. On the desktop side, we have Windows, Mac OS, and various Linux distributions like Ubuntu, Linux Mint, and Kali Linux, along with Android for mobile devices. On the enterprise and server side, we have Chrome OS, Red Hat Enterprise Linux, Debian, FreeBSD, and Solaris. Notice that many of these are actually built on similar underlying technology. For example, several Linux-based systems can run GNOME, XFCE, or KDE as their desktop environment. So, while the branding looks different, there's often shared DNA underneath. An operating system does not operate in a vacuum. It manages a real physical hardware. On the left, you can see a typical macOS desktop. This is a layer user actually interacts with. On the right, we have opened up the case to look at what's actually inside. The CPU executes instructions and processes data. Memory temporarily holds data and instructions currently in use. The motherboard is the main circuit board that connects every component together. The GPU handles graphical processing and display output. The hard drive permanently stores your program and files. Power supply unit converts AC power from the wall into the DC power the computer's components need. The I/O ports allow you to connect peripheral like your mouse and keyboard. Everything you do on that friendly desktop on the left is ultimately powered by the OS coordinating all of these hardware on the right. Different desktop environments. Here a quick visual comparison of what different operating systems actually look like day to day. Top left we have Windows with its familiar startup menu. Top right macOS with its clean dock at the bottom. Bottom left Linux distribution. You can see it's running Firefox. And bottom right Chrome OS, which is built almost entirely around the Chrome browser. Even though these all look different on the surface, remember underneath every one of them there's an operating system doing the exact same fundamental job, managing hardware, running programs, and giving user a convenient way to interact with the machine. Now let's categorize operating systems by where they are used, because context really changes what an OS needs to prioritize. Desktop and laptop operating system like Windows, Mac OS and Linux prioritize usability and a rich set of features. Mobile operating systems, Android, iOS and Harmony OS are optimized for touch interaction and battery efficient. Server operating systems like Windows Server and Red Hat Enterprise Linux prioritize reliability, security, and handling many simultaneous users. Embedded operating systems such as Embedded Linux and VxWorks run inside devices like applications and industrial equipment where resources are limited and the OS needs to be lightweight. Real operating systems or RTOS like RT Linux and QNX guarantee that tasks complete within strict time limits, which matters enormously in things like medical devices or automotive control systems. And finally, there are specialized and less common operating systems like Haiku, React OS, and Plan 9, which serves a niche or experimental purpose. Let's go a little deeper into real-world example with each category. For desktop and laptop operating systems, Windows alone spans multiple versions: Windows 10, Windows 11, and even Windows 7, which technically isn't supported anymore but still has user out there. On the Apple side, we have had macOS Ventura, Monterey, and Big Sur. And Linux offers a huge range of distributions: Ubuntu, Fedora, Debian, CentOS, Red Hat Linux, Enterprise Linux, Linux Mint, and Arch Linux, just to name a few. For mobile and Android, has multiple recent versions like Android 13 and Android 12, and iOS similarly has iOS 16 and iOS 15. For servers, you will commonly see Windows Server 2022 and 2019, along with Linux-based server distributions like Ubuntu Server and CentOS Team. There's also a whole family of Unix-based systems still in use today: AX from IBM, HPX from Hewlett-Packard, and Solaris from Oracle. And rounding things out, embedded systems use things like Embedded Linux and Tizen, while specialized systems include FreeBSD and OpenBSD, Haiku and React OS. You don't need to memorize this entire list. This point is simply to see just how broad and diverse the operating system landscape really is. Let's zoom out and look at the computer system as a set of layers. At the very top, we have users. This could be one person or many, shown here as user 1, user 2, user 3, and so on. Below the user is a layered system and application program, things like text editor, data related tools. Below that side, the operating system itself, the layer that actually manages everything happening above it. And at the very bottom, we have computer hardware, the physical machine that everything ultimately runs on. This layered view is really important to internalize. User never touch hardware directly. Every request flow down through programs, through the operating system, and only then reaches the hardware. Let's formalize this into 4 distinct components that make up any computer system. First, hardware. This provides the basic computing resources, the CPU, memory, and I/O devices. Second, the operating system which controls and coordinates the use of hardware among various applications and users. Third, application programs. These defines a way in which the system resources are used to solve the computing problems of users. Think word processors, compiler, web browser, database system, and even video games. And fourth, users, which could be people, machine, or even other computers making requests. Together, these four components form the complete picture of a computer system, with the operating system sitting right in the middle, coordinating everything. Interestingly, what an operating system does really depends on your point of view. There are two main perspectives here, the user view and the system view. From the user view, people generally want convenience, easy of use, good performance. But this varies quite a bit depending on the setup. On a shared computer like a mainframe or microcomputer, the OS has to keep all users happy simultaneously, balancing their computing needs. On dedicated systems like workstations, users typically have their own dedicated resources, but they still frequently rely on shared resources from servers. Handheld computers, being resource poor, are optimized heavily for usability and battery life. Some computers, like embedded systems in devices and automobiles, have little or no user interface at all. From the system view, things look quite different. Here, the OS is seen as a resource allocator, managing CPU time, memory space, file storage space, and I/O devices. It's also a control program, managing the execution of user program to prevent errors and improper use of computer. So, depending on who you ask, a regular user or a system engineer, you will get a genuinely different answer to what does an operating system do. Let's crystallize this into two clean definitions. First, the OS is a resource allocator. It manages all the resources on a system and it dedicates between conflicting requests for efficient and fair use of those resources. Imagine two programs both waiting the CPU at the same time. The OS decides who gets it and for how long. Second, the OS is a control program. It controls the execution of programs to prevent errors and the improper use of the computer. Without this control, one poorly written or malicious program could crash the entire system or interface with the others. These two definitions, resource allocator and control program, really capture the dual role the operating system plays at all times. Here's a more precise technical definition. Operating system is the one program running at all times on the computer, and this core program is usually called the kernel. Look at this diagram. It shows a simple layered structure. At the very bottom is the hardware sitting directly on top of it is the kernel, the heart of the operating system. And above that, we have the various programs that runs on this system. Now, along with the kernel, there are two other type of programs worth distinguishing. System programs are associated with the operating system, but they are not necessarily part of the kernel itself. Think of utilities and background services. Application programs, on the other hand, include all programs not associated with the operation of the system itself. These are the everyday app you and I use, like browser or word processor. So remember this hierarchy. Hardware at the bottom, the kernel directly above it has the true always running core, and the system and application program built on top. Now we are moving into the second major part of today's session, computer system organization. This topic breaks down into three areas that we will cover one at a time: computer system operation, storage structure, and I/O structure. Let's start with the computer system organization. A modern general purpose computer system consists of one or more CPUs along with a number of device controllers, all connected to a common bus that provides access to shared memory. Each device controller is in charge of a specific type of device. For example, disk drives, audio devices, or video displays. It is important to understand that the CPU and the device controllers can execute in parallel, but they are also computing with each other for memory cycles since they all share that same memory bus. This diagram illustrates that shared architecture, multiple components all connected through a common pathway to memory, working simultaneously but sharing that critical resource. Let's talk about how computer actually starts up. This is where the bootstrap program comes in. When a computer is powered up or rebooted, it needs to have an initial program to run. After all, nothing is loaded into memory yet. This bootstrap program is stored within the computer hardware in read-only memory or ROM, so it's always available even before anything else had loaded. The bootstrap program has two critical jobs. It must know how to load the operating system and how to start executing that system, and it must locate the operating system kernel and load it into memory. Once the kernel is loaded and executing, it can finally start providing services to the system and its user. Look at the diagram. ROM folds the bootstrap program, which reads and loads the OS into RAM. From there, the OS takes over and starts device driver to get the whole system running. Beyond the kernel itself, some services are provided outside the kernel by system programs, often called system processes or system daemons, that get loaded into memory at boot time and run the entire time the kernel is running. Now let's talk about interrupts, which are absolutely central to how operating systems work. Hardware may trigger an interrupt at any time by sending a signal to the CPU, usually by way of system bus. Software can also trigger an interrupt by executing a special operation called a system call. When the CPU is interrupted, it stops whatever it is doing and immediately transfers execution to the fixed location. Every computer design has its own specific interrupt mechanism, but a common approach is to use an interrupt vector, a table of pointer to interrupt routines, so the CPU knows exactly where to jump for each type of interrupt. Let's visualize this with a timeline diagram. At the top, we see the CPU's activity is executing the user process, shown as a flat blue line. Below that, we see the I/O device state, either ideal or transferring data. Watch what happens at the I/O request mark. The I/O device switches from ideal to transferring. The CPU keeps running the user process the entire time. It doesn't just sit and wait. Then, a transfer done, the I/O device signals completion via an interrupt. You can see the CPU line dip briefly to handle that I/O interrupt processing, and then it returns right back to executing the user process. This is the whole point of interrupts. The CPU does not waste time waiting around for slow devices. It keeps doing usual work and only pauses briefly when a device actually needs attention. Now let's move to the storage structure, understanding the different types of storage in a computer system and how they are organized. At the very top of the hierarchy, we have registers, the fastest, smallest storage located directly within a CPU. Next is cache, small, fast memory sitting between the CPU and main memory, which significantly improves performance by keeping frequently used data close to the hand. Then we have main memory. This is volatile, meaning it loses its contents when power is lost, and it serves as the primary storage for actively running programs and data. Below that, solid state disk, non-volatile, faster than magnetic disk, and built using flash memory. Then magnetic disk, non-volatile, large capacity but slower than SSDs or traditional hard drives falls into this category. Optical disc, non-volatile, typically used for distribution and backup like CDs and DVDs. And finally, magnetic tape, non-volatile, used mainly for archival storage. It has very high capacity but access is slow. Notice the pattern here. As we move down this hierarchy, storage generally gets slower, cheaper and larger. This is exactly how storage system is organized by speed, cost and volatility, forming a pyramid with the fastest, most expensive storage at the top and the slowest, cheapest storage at the bottom. Let's now look at I/O structure. How interrupt and output actually happens in a computer system. I/O management is absolutely crucial for system reliability and performance, largely because of how varied device types can be. A keyboard behaves very differently from a hard disk, which behaves very differently from a network card. In terms of system architecture, we have CPUs, device controllers, and a common bus connecting them. Device controllers manage specific device types and typically have local buffers and special purpose registers of their own. The device driver provides a uniform interface to the device, and it's the piece of software that actually communicates with the device controller. Here's the general I/O operation process, step by step. First, the device driver loads the register into the device controller. Second, the device controller determines what action to take, for example, a read or write. Third, the data is transferred to or from the device through the controller's local buffer. Fourth, the device controller signals completions via an interrupt. And fifth, the device driver returns control, data and status back to the operating system. This five-step cycle happens constantly every time your computer reads a file, saves data, or communicates with any peripheral. Interrupts can feel abstract, so let's use a real-world analogy, a hospital. Imagine a doctor treating a patient. Doctor is examining patient A. Suddenly, an emergency patient arrives. The doctor passes the current consultation, treats the emergency patient, and then returns to the patient A to resume where they left off. Now map that onto a computer system. A doctor is a CPU, the regular patient is a program, the emergency patient represents an interrupt, the emergency treatment is the interrupt service routine or ISR, and resuming the consultation is the same as the CPU resumption program execution. This is exactly what happens inside your computer thousands of times per second. The CPU is doing one thing, something urgent comes in, it briefly switches over to handle it, and then it returns right back to where it was doing before. Let's make this every more concrete with the everyday example. Ask yourself, is this an interrupt? Your phone rings while you are watching YouTube? Yes, that's an interrupt. A WhatsApp notification pop-ups? Yes. A doorbell rings while you are studying? Yes. A teacher asks you a question during an assignment? Yes, that's an interrupt too. A fire alarm goes off? Absolutely. Yes. In every one of these cases, whatever you are doing, get past, you handle the more urgent event, and then just like the CPU, you go back to what you are doing. This is precisely the same logic your computer uses internally, just applied to everyday life. Let's go a bit deeper into I/O structure with the two important techniques: interrupt-driven I/O and direct memory access or DMA. Interrupt-driven I/O is suitable for small data transfers, but it creates high overhead when you are moving large amounts of data because the CPU has to interrupt it repeatedly for every small chunk. That's where direct memory access comes in. DMA transfers data directly between the device and memory without the CPU needing to babysit every single byte. This dramatically reduces CPU involvement and generate far fewer interrupts, which make it much more efficient for large or bulk transfers. On the high-end systems, we also see switch architecture, which allows concurrent communication between multiple components simultaneously, and enhanced DMA, which becomes even more efficient when paired with that switch architecture. The overall theme here, as data volumes grow, system evolve smarter techniques to keep the CPU free to do other productive work instead of getting bogged down managing IO. Now we are moving into the final major topic of today's session, computer system architecture. Let's start by classifying system based on how many processors they have. A single processor system is defined as having only one general purpose CPU. A multiprocessor system requires multiple general purpose CPUs. Here's an important classification. The presence of special purpose microprocessors like the ones controlling your disk drive or keyboard does not classify the system as multiprocessor system as long as there's only one general purpose CPU doing the main computational work. Special purpose does not count toward this classification. It is specially about general purpose processing power. Let's dig deeper into single processor system. The main CPU executes a general purpose instruction set, including instructions from user process. This is the workhorse of the system, but the single processor system also contains special purpose processors. These might be device specific like disk, keyboard, or graphics controller, or more general purpose like dedicated IO processors. These special purpose processors have a limited instruction set, and critically, they do not run user processes. That's not their job. They are typically managed by the operating system. For example, a disk controller microprocessor receives a task from this main CPU, manages its own disk queue, and runs its own scheduling algorithm, which reduces the main CPU's overhead significantly. Similarly, a keyboard microprocessor converts your keystrokes into codes that the CPU can understand. In some cases, these special purpose processors operate completely autonomously and are not managed by the operating system at all. They just quietly do their job in the background. Now let's talk about multiprocessor systems. Systems with two or more processors in close communication, sharing the computer bus, and sometimes even sharing the clock, memory, and peripheral devices. There are two major types. First, asymmetric multiprocessing, where each processor is assigned a specific task. In this setup, a boss processor controls the system while the other processor either look to the boss for instructions or carry out predefined tasks. This is often called boss-worker relationship, where the boss processor schedules and allocates works to worker processors. Second, symmetric multiprocessing, often abbreviated SMP. Here, every processor performs all tasks within the operating system. All processors share physical memory equally. Examples of system using this approach include AIX and Unix. Multiprocessor system offers some clear advantages. Increased throughput, since more work gets done in parallel. Economy of scale, since sharing resources across processors is often cheaper than running separate systems. And increased reliability, since if one processor fails and others can often continue operating. Let's continue with the two more important concepts, multi-core processor and blade servers. A multi-core processor is a chip design that includes multiple computing core on a single chip. This offers real advantages. It's more efficient than using multiple chips with a single core because on-chip communication is faster than communication between separate chips. It also uses significantly less power than running multiple single core chips would. One important clarification: multi-core systems are indeed multiprocessor systems, but not all multiprocessor systems are multi-core. Multiprocessing is the broader category, and multi-core is just one way to achieve. Now, blade servers. This is a relatively recent development where multiple processors, boards, I/O boards, and networking boards are placed in the same chassis. Each blade processor board boots independently and runs its own operating system, which gives you a dense, modular way to pack many independent systems into a single physical unit. Let's look at clustered systems. These gather together multiple CPUs and are composed of two or more individual systems or nodes joined together. Each node might be a single processor system or a multi-core system on its own. What defines a cluster is that these nodes share storage and are closely linked via a local area network. There are two types of clustering: asymmetric clustering, where one machine sits in hot standby mode while the other is actively running applications. The hot standby machine does nothing but monitor the active server, and if that server fails, the hot standby machine takes over and becomes the active server. Symmetric clustering, where two or more hosts are actively running applications while simultaneously monitoring each other, so there is no single ideal backup machine. Some clusters are specifically built for high performance computing or HPC, but for this to work, applications must be specialized, written to take advantage of parallelism. Some clustered systems also use a distributed log manager or DLM to avoid conflicting operation across nodes. Let's look at a detailed architecture diagram tying together everything we have discussed about single processor system. At the center, we have a processor or CPU containing the control unit, the arithmetic logic unit, and the register, all working together internally. To the left, main memory RAM connects to the CPU. To the right, I/O modules connects out to peripheral like a monitor, keyboard, mouse, disk, and printer. Notice three buses running along the bottom, connecting everything together. The addresses shown in red, the data bus is shown in blue, the control bus shown in green. These three buses are how every component is in the system communicates. Addresses tells you where the data carries the actual information, and the control signal coordinates when and how that communication happens. This diagram is really complete, concrete picture of everything we discussed conceptually a few slides ago. Now here's a multiprocessor version of that same architecture. Instead of single processor, we now have processor 1, processor 2, all the way up to processor n, each with its own control unit, arithmetic logic unit, and a register. All of these processors connected through an interconnection network or a system bus. This could be a shared bus, a crossbar, a ring, or a mesh topology depending on the system design. Below that shared interconnect, we have a main memory and I/O controller interface, an optical shared cache, and a system controller, which handles things like the interrupt controller, timer, DMA controller, and arbitration logic, making sure multiple processors don't collide when accessing shared resources. This is the direct visual extension of symmetric multiprocessing concept we discussed earlier. Multiple processors all sharing memory and I/O through a common, carefully coordinated interconnect. And finally, here is the detailed architecture for clustered system. We have node 1, node 2, up through node n, and each node is essentially a complete small system on its own, with its own CPU containing multiple cores, its own cache, its own local RAM, and a network interface acting as the chip adapter. All of these nodes connect through a high-speed interconnect. Technologies like InfiniBand or high-speed Ethernet are common choices here. Below that shared network, we find shared storage, often a SAN or NES setup. A cluster management node responsible for things like resource monitoring, job scheduling, and failover management, network services like DNS and load balancing, and shared I/O and peripherals. Compare this to the single processor and multiprocessor diagram we just saw. Notice how clustering takes the idea of sharing resources a step further, connecting entire independent systems together rather than just a processor within one machine. And that brings us to the end of session 1. Let's do a quick recap. We covered what an operating system is and its three core goals: the layered structure of computer system, a computer system operation including bootstrap program and interrupts, storage and I/O structure, and finally computer system architecture from single processor system to multi-processor system to clustered system. This is genuinely the foundation for everything else we will cover in this course. So make sure these concepts feel solid before we move on. Thank you so much for watching. If you found this helpful, feel free to like, subscribe and drop any questions in the comments. I'll see you in the next session.